Thank you for coming to our talk. Today we're going to talk about how to secure applications through defense in depth by building a trusted software supply chain and then having continuous monitoring on your Kubernetes clusters. So a quick introduction. I'm Steven Terrana. I'm a lead technologist at Booz Allen Hamilton. We're a federal consultancy, so I do a lot of legacy IT modernization within the government space.
And I'm Michael Ducy. I'm one of the maintainers of the Falco project. I do a lot in the world of DevOps, help organize a few DevOps days throughout the world, and also help with SIG security and other things in the CNCF.
All right, so vulnerabilities. This is a representation of the typical vulnerability lifecycle, right? So if you think about the average vulnerability, there's going to be a time when that vulnerability is introduced into your environment. There's going to be a time when an exploitation for that environment is, for that vulnerability is discovered. At some point, you're going to realize that your environment is compromised, and then presumably after that, you're going to patch that vulnerability, right? So that time between when that exploitation is discovered and when you actually patch it is when you're most susceptible to being compromised. So what can we actually do about this? Through DevSecOps and integrating security into your software development lifecycle, you can shrink that time from when an exploitation is discovered to when you're able to identify that it's in your environment and then subsequently patch it. All right, so everyone I've ever talked to has a different definition of DevOps or DevSecOps. So this slide serves to level set what exactly I'm talking about when I say DevSecOps. The too long didn't read of this slide is that it's all about shifting left security and incorporating it into every step of the software development lifecycle. Traditionally, DevOps was about getting application developers and operations engineers to work together more effectively through automated testing, infrastructure as code. So we're able to quickly and reliably deploy our code. We're fairly confident that it's going to work through automated testing. But we were still experiencing bottlenecks when it came time to actually deploy to production. And that's because we never actually pulled in the security team. So DevSecOps is all about incorporating the security team's requirements. There's a whole bunch of different kinds of security testing that you can incorporate, like application dependency scanning, making sure third-party libraries are secure, static code analysis, making sure that you haven't hard-coded IP addresses or passwords into your code base. Dynamic application security testing is a mouthful of a way to say penetration testing, so actually attacking your deployed applications and seeing if they're susceptible to common exploitations. With containerization comes the container image. So there's container image scanning to make sure that if we're pulling images off Docker Hub with no clue who actually built them, that they don't have known vulnerabilities or Bitcoin miners. Vulnerabilities in general come in two flavors. You've got vulnerable packages and vulnerable configurations. So a lot of the container image scanning tools out there will help you out with the compliance side, which is making sure that you haven't configured your containers to run as root, making sure that you're compliant with different fairly regulated guidelines like NIST or Secure Technical Implementation Guides if you happen to be working in the federal space like I primarily do. And in that same vein of compliance, you've got accessibility assurance, so making sure that the applications we're building are accessible and 508 compliant. It is important to note there's no tool out there that's going to tell you that you are 100% 508 compliant, but what they can do is tell you if you're not. All right, so if you included an image on your website, for example, that doesn't have an alt text, that's a pretty black and white, easy to figure out 508 compliance issue. So a lot of the tools that can help you with this are primarily trying to give developers fast feedback on accessibility issues on their application so that those that are doing the manual testing can focus on the more complex aspects of compliance. So all of the security testing is in addition to all of the other kinds of quality assurance testing that the industry's been doing for a couple of years now. So things like unit testing, functional testing, browser-based test automation, pull a word out of the dictionary and add testing to the end of it. If you're supporting enterprise scale pipeline development, so you're a centralized DevOps team helping support CICD pipelines for multiple applications at the same time, or if you're building a platform to host microservices, it's likely that applications in your portfolio are leveraging different tools, right? So your front-end applications might be doing unit testing with something like Karma or Jest, whereas backend applications, if they're Java, might be using JUnit. You could have a Python backend. Some teams in your organization might be using SonarQube for static code analysis. Other teams might be using Fortify. So the current CI/CD landscape out there is primarily targeted at application-specific pipelines. Most of the time, you get an artifact in your source code repository that outlines as code what your software delivery processes look like. So when a developer does something in GitHub or whatever your source code provider is, what does that mean from a pipeline perspective? So when you're supporting, for example, a 60 microservice-based application, that means that you have 60 different pipelines that exist, right? So let's say you're using Jenkins, and you have a Jenkins file that you probably copied and pasted across all of your 60 different source code repositories, and then tweaked it to make sure that it's compatible with whatever specific tools are being used in that repository.
From Stack Overflow, no less.
From Stack Overflow. We have all Googled SonarQube plus Jenkins and found the 6 lines of code to do a static code analysis. If you want to make a change to that, because we're all striving to be continuously improving our software delivery processes, that means you have to go open 60 pull requests, right? And you need to work with these application development teams to coordinate a migration to a new version of the pipeline. And having to have done this myself, it can be an extremely cumbersome process that ultimately introduces so much technical debt that you kind of just leave the pipeline as is. You don't want to add new tools, and it really starts to stagnate your ability to continuously improve. And at Booz Allen, we do a lot of application modernization. Every project that we're working on needs a pipeline. So this duplication of effort across applications takes place within a single project. It hampers your ability to continuously improve. But then we're also reinventing the wheel across every project that needs a pipeline. So every DevOps engineer at Booz Allen would go to Google or Stack Overflow and find the same code snippet and introduce it. So about 3 years ago, we set out to figure out, like, how can we make this go faster? When a project starts up, not everyone is a Jenkins expert. I know way more about Jenkins than I'd like to admit, and really should have to. It would take 4 to 6 months to find all the right Stack Overflow snippets to tie together. So we wanted to drastically improve how quickly we could deploy pipelines, while also being able to introduce a level of organizational governance. Right? One of the biggest issues with those 60 different Jenkins files is that you don't actually know they're all doing the same thing. Right? If an organization says you need to do container image scanning, you need to do penetration testing, you're really just trusting that all of the different development teams have implemented a pipeline that meets these organizational standards. And we wanted to figure out how could we take pipeline development from what you see on the screen, which is every development team has a pipeline that largely follows the same steps. It doesn't matter if you are, doesn't matter which tools you're using, the process is largely the same. You're gonna build something, you're gonna package it somehow, you're gonna test it, deploy it, scan it. So that's really the revelation that we came to, was what if we could create pipelines in a tool-agnostic, templated way to take pipeline development from what you see on the screen to something that looks a little bit more like this, where you have a centralized DevOps team that's supporting multiple applications. They maintain a tool-agnostic, templated workflow that outlines the business-approved software delivery processes. This makes it really convenient when working with security teams, making sure that their requirements are represented, because they can be stakeholders in coming up with this pipeline template. That team would likely consist of all of the different stakeholders that go into your software delivery processes. So that includes like SecOps engineers, DevOps engineers that know how to write pipelines, QA engineers that can speak to test automation. So what if we had a centralized team that could define this tool-agnostic template? So let's say you wanted to build, scan, deploy, and test. The different tools that are going to perform these actions of building, scanning, deploying, testing can just be modularized into a different pipeline library, we call it. So if I wanted to do a scan with static code analysis as a scan with SonarQube, there'd be a SonarQube library. that introduces a static code analysis step to my pipeline, and there'd be a Fortify library that introduces a static code analysis step to my pipeline. So alongside your pipeline template, you get a pipeline configuration, which just tells Jenkins, or the pipeline, what tools am I using to actually build this DevSecOps pipeline. There's some organizational governance there, so if at the top level you have some tools that you want to enforce everybody is using, you can consolidate those common controls to a centralized repository, but still give development teams the flexibility they need to customize the pipeline to introduce different tools. Right? So that centralized pipeline definition of build, scan, deploy, and test can turn into what you see at the bottom of the screen, which is building with Maven, scanning with Fortify, deploying with Ansible, and testing with Selenium. Or it can mean building a Docker image or container image, scanning it with SonarQube, deploying it with Helm, and testing an API with something like Rest Assured. So let's see what this looks like in practice. If I head over to my Jenkins instance. So let's take a look at, there's a couple different use cases here. We're going to show the simplest first.
Make the font bigger.
Make the font bigger. I will do that. Thank you, Michael. Can everyone see okay? Seeing general nods of agreement.
Yes.
So this is a pipeline job in Jenkins. We wrote a Jenkins plugin called the Jenkins Templating Engine, which achieves a lot of what I'm talking about. The ability to take that Jenkins file that's application specific out of individualized source code repositories, define it in a central place, and allow teams to pull in their unique configurations. So what you see on the screen is an example of a simple pipeline template. They can get a lot more complex if you want to map your pipeline to your branching strategy. So when you do merges to the develop branch, it does something different than merges to the master branch. But for the sake of demonstration, let's assume you've got a linear pipeline that's going to do build, some static code analysis, and it's going to deploy to a dev and prod environment. Alongside that pipeline template, you get a pipeline configuration file. So this is going to implement that pipeline template, if you will. So there's a library section that's going to pull in the specific tools that you're using to implement the pipeline. So in our case, these libraries are going to do print statements just because we want to really demonstrate and communicate what pipeline templating looks like. So they're going to do some print statements to say which library contributed which step. Alongside your libraries, you can dynamically define application environments. Every project I've ever worked on has a different number of application environments. They give them unique names. I've been on a project where dev was called Squirtle. I don't know why. But from your configuration file, you can dynamically define these app environments and store whatever environmental context you need to know in order to perform deployments to those specific environments. So if I apply this configuration, zoom out for a second, and click build, I'll look at a finished one so we don't have to wait for it to load. But what we're going to notice is that at the beginning of the pipeline, JTE, Jenkins Templating Engine for short, is going to initialize the pipeline. So we're going to go pull in all the different libraries that implement these steps. These libraries are just modularized tool integrations. So they're stored in a source code repository. They're just directories in your repo. So for example, we loaded the Maven library. There's a build.groovy step. That turns into the build step when you load it in your pipeline. So if we take a look at this build step, it's just Jenkins pipeline as code. So the framework introduces some syntactic sugar to make it easier to write libraries and access configuration from your config file. But JTE is really just a different way of organizing your pipeline code to achieve this pipeline templating and reuse. So if we go back over to Jenkins, we loaded all the requisite libraries that we talked about. The stage view will probably give us a easier to parse representation, where we say that we did a build with Maven, we did SonarQube static code analysis, and then we deployed to a dev and production environment. So in practice, you're not going to want to put that information in your Jenkins UI. You're going to store it in your repository most likely. So this is a multi-branch project, which means it's going to automatically create jobs for every branch and pull request in your pipeline. Here, the Jenkins file has been pulled out of the repository. We can store it right alongside our libraries or in a separate repo. Doesn't matter. We can define that pipeline template externally, alongside a pipeline configuration that just says, this is what's required by the organization. We have this nice key that says merge equals true, which is going to allow the application to just add in the Maven library. And when we build it, every branch of this pull request, of this repository, excuse me, is going to do the exact same thing. So now the real power comes when we want to scale this up to multiple applications. So the idea is the same. What if I had a Gradle application instead of a Maven application? All I would want to change is the implementation of my build step for this example. So the Maven application would have a pipeline configuration file that says that it's pulling in the Maven library. We can take a look at this repo. All it says is, hey, I'm using Maven. We can go take a look at the Gradle repository, and they just say that they're using Gradle. But if we go look at Jenkins, when you look at the Gradle application, the pipeline pulled in the Gradle library, so we had a Gradle implementation of our build step. We can go over and take a look at the Maven library and see that it's the same it's using Maven, right? So what's the big picture here? If we go back to our slides. So what are the main benefits of this? Organizational governance. You don't have to copy and paste Jenkins files anymore. You don't all have to figure out how to do static code analysis with SonarQube by Googling it and copying and pasting it. So organizational governance, centralize your pipeline definition to a common place and define processes that are approved by your security teams, regardless of specific tool implementations across your entire organization. Optimizing pipeline code reuse. So these libraries are reusable and open source. At Booz Allen, we've seen pipeline development decrease by 97% for new projects if you're using existing tool integrations because the work's already been done. We can reuse these libraries across all the pipelines that we're developing to drastically speed up pipeline development from something like 4 to 6 months to 4 to 6 days if you're following a happy path. And then simplifying pipeline maintainability. In my humble opinion, it's a lot easier to manage a centralized pipeline template with modularized tool integrations than it is to keep straight copied and pasted 60 different versions of a pipeline as code artifact and handle migrations of improving that over time. So applying that to security, this means that you can now standardize your software delivery processes to do things like container image scanning, application dependency scanning, and you can still give teams the flexibility they need to while having the assurance that they're all going to follow the same process. So we can make that even better, and Michael is going to talk to us about how we can add some defense in depth. So we've made sure that our applications are secure by implementing these security testing. How do we still make sure that we're safe in production?
Thank you, Stephen. So if we think about this pipeline, the one thing that you want to do when you start looking at your pipelines in this way is that starting to remove areas of waste. And areas of waste tend to be areas where you spend a lot of time, right? So the pipeline definition that he showed here is actually really, really useful exercise to do, to actually draw out and put times on each one of those areas, because then it starts helping you understand where you need to optimize. But also when you look at the entire life cycle like this, we're like, how can we reduce this time to where we actually detect the exploitation or discover the exploitation, a vulnerability has been discovered, and then we've been hacked, or we have to go through this entire cycle again to actually go and actually patch our applications. And the challenge is with containers and ephemeral workloads, so we did a study at Sysdig recently, and containers are lasting on average about 5 minutes. And so in a container that only lasts 5 minutes, how can you actually discover that it was breached? Someone was able to do data exfiltration and other things like that as well. So with that, we'll introduce Falco. And so what is Falco? So it's a behavioral activity monitor. It detects suspicious activity defined by a set of rules. In non-marketing speak, you can call it a host intrusion detection system. But what makes us unique is that we're focused on container and orchestrator support. So we have native integrations into Docker, Cryo, Containerd, Kubernetes to actually pull back the metadata information from those sources, combine that with what we're actually seeing on a system call level and in the Kubernetes audit event log level, and using that to actually create very, very rich and granular rules. And when we detect something that's abnormal, we'll alert via various methods and it's open source. So we're a CNCF Sandbox project. You can contribute improvements to the project or rules as well. Speaking of that, we're also going up for incubation as well, and we have an incubation proposal up. So hopefully within the next month or so, once everyone gets past KubeCon and Thanksgiving, we'll be moving into incubation, which means the CNCF will be supporting us even more with infrastructure and other things like that as well. So it's an exciting time for the project, and if you're wanting to contribute to a project, I highly encourage you to look at Falco or JTE as well. So why does anomaly detection get easier in a containerized world? And I think it gets easier because we have this abstraction, and we can use this abstraction of a container or a pod or a namespace or a definition of basically what we think should be going on in that abstraction. So since containers are supposed to be one process per container and it's an isolated process, the processes, as I say, are scoped as to what's expected. So you know what processes are going to run, you know what files they're going to manipulate, you know what directories they're going to touch, you know what ports they're going to listen on. And inside of a container, it should be very, very easy to define all of the activity from a system call level that's going to take place when you deploy it. The challenge is that containers are immutable, so the container image itself, if you change something, if you change the configuration and rebuild the container, the SHA changes, so it's a new container. However, when the container launches, that environment can still be manipulated. Very few people run containers in a read-only root file system mode. And so if somebody actually breaches the container, they can start to actually add in things. So they can do an apt-get upgrade, they can do an apt-get install, and starting to add in the tools that they need to actually go and do data exfiltration or explore your environment and move laterally or horizontally. And so how do you, in this environment, can you detect abnormal behavior in these containers that are very, very short-lived? So you do that with Falco. So let me talk about the architecture real quick. What we do is we take different pieces of information and we run them through the Falco rules engine. So we can tap into system calls using either a kernel module, which is kind of our legacy way of doing things, and then our next generation way of doing things is eBPF. We're actually giving away books, Linux Observability with BPF at the Sysdig booth. The author of the book is giving those away. So BPF is an area that we do a lot of work in and a lot of study in as well. And then we can also take things like Kubernetes audit events and then Kubernetes metadata, combine them together into our rules engine, and then push out alerts. And I'm going to talk about the BPF instrumentation real quick. So the way that this works is essentially you deploy, you can either deploy Falco directly on your Kubernetes nodes or your hosts. It doesn't need to be running Kubernetes. We can work on a standard Linux system as well, so you can use this as a generic host intrusion detection system if you want. In a Kubernetes cluster, what you typically do is deploy this as a daemon set. The eBPF program gets installed on that node's kernel, and that allows us to get an event stream of all the system calls that are taking place and going through the system. So because it's a shared kernel and we've installed our instrumentation in the kernel, we can then see everything that's happening inside of your containerized workloads. So we can see what files are opened up, what network connections are opened up, what processes are spawned, what processes are doing, what system calls they're calling, and so forth. To give you a little bit broader example of the architecture, we'll also pull in Kubernetes audit logs, which I'll talk about here in a second. And then we have a whole bunch of different destinations that we can actually send out alerts to. One of the things that we're focusing on, if you're an expert in the space or if it interests you and you want to find a project to work on, is we're really building out this output API and our output interface. We're going to base everything on gRPC, and then like you see with the Falco Client Go and Prometheus, we're going to be expanding out the outputs that we can do via this gRPC connection. It's an asynchronous, non-blocking connection, and so that streaming server will help us do a lot of different workloads of what we can actually do with the events, which I'll talk about here towards the end. So let's look at the rules and how the rules look so that we can understand them. So apologies to those on that side of the room. I promise to walk over here next time.
I can point.
All right, thank you. So we have a couple constructs in our rules. So we have macros, lists, and rules. So a list is essentially just an array. We can see that we've named it vendors, and then we have the items in the array. It can just be one item or one element if you want. And then you can see here we have a macro, and a macro is essentially a shortcut for a rule condition. So it just makes it easier to write something over and over and over again. The Falco default rule set provides lots of macros for you. So if you wanted to catch an outbound connection, all you need to do is write outbound, and that macro is available to you, and it will detect all outbound connections automatically. So here we're going to say our directory is in binders. So basically, our directory that's set in the system call information is one of these four. And so what's nice here is when I decide to start storing binaries in opt your company name or your application name bin, all I need to do is go and update the list, and I don't need to update my macro or my rule. And then we can see the rule here. We have I'm a binder, and event direction is the system call is returned. That's kind of not important, so we'll just skip it. I've opened something for writing in this directory, and I'm not a package management process. What will happen is Falco will alert. You'll get the username, you'll get the command, and the file name of what was actually being manipulated underneath that directory. Make sense? So there's a whole bunch of different metadata or different what we call field classes that you can pull in. So we have things like the Kubernetes metadata information here, container metadata information as well. And so you can use all of this information to say, I'm a namespace, or I'm running in this particular namespace, I'm a particular pod with these particular labels. Apply this rule only to me, depending upon maybe I'm running in a namespace that has particular compliance requirements for PCI or something like that. So here's another rule to give you an example of incorporating that metadata information. So don't run this in production because you'll get a lot of false positives, but it's good for an example. So I've spawned a process with using the exec.ve system call, and then my container image starts with node, and my proc name does not equal node. So basically, anytime that a container runs a process other than the node application, we'll get an alert that the container is doing something abnormal. We have a bunch of different rule sets. If you go to securityhub.dev, I don't have a slide on this, so this is the only time I'm going to say it, securityhub.dev. You can see a whole bunch of different Falco rules that you can download for common applications. And one of the things that we're working on, one of our team members, Chris Nova, is working on is Falco CTL, to where you can automatically go and do Falco CTL rule install, and you'll be able to download those rules directly from Security Hub. So another area that we're looking for contributions and help on. Now we can also look at Kubernetes audit events as well. And so Kubernetes audit logging is something that came out in Kubernetes 1.11. It's getting more and more mature. And what you can do is basically get a chronological record of every single change that goes through the API server. So anytime that someone hits the API server, you'll get 4 different options that you can choose of whether if that request just came in or whether if it was actually completed and was successful. And that's controlled with what's called audit policy. And then once you have this audit policy, you can then take that and ship that off to some other location to do processing on it. What we'll do is we'll actually apply the Falco rule set to this information. And the different ways that you can configure this is log files, webhooks. These 2 methods aren't available if you're using something like GKE or AKS or a managed Kubernetes service where you don't have access to the master. This is changed on the master. So what the Kubernetes community did is they created something called audit syncs, where you can actually dynamically control this by putting a JSON document up into the Kubernetes API server. So here's what an audit event looks like. And in this audit event, you can see that the response was complete. We deleted, the Minikube user deleted the namespace foo. And then we get an ID for that as well, and we can see that the authorization service allowed this request. So we extended the Falco language to include all of these different values. The other interesting thing is that if Kubernetes ever changes what this JSON document looks like, we'll still take it and parse it, and we can actually pull any value out by just calling JEvent value and the JSON pointer. This also allows us to implement new input sources as well. So after we get done with the output API, we're going to be working on the input API to allow you to have more sources where you can actually write these rules and extend the Falco language for detecting things. So here's what a Kubernetes audit rule looks like, and then I'll jump into the demo and then we can wrap up. So we have a macro here that says contains private credentials. We can see we have the AWS access key, so we're just looking for these strings. And while this is not going to stop state-level actors, right? But normally your breaches and things like that happen because Bob in accounting made an S3 bucket public, or Bob in accounting went, and no offense to Bob, he's just trying to do his job, but went and posted things in a GitHub repository they weren't supposed to, or unencrypted secrets and other things like that, right? So we now have a macro called a config map, so KA target resource config maps, meaning that we're manipulating the config map through the API. We're doing a create, update, or patch, so any one of these actions, and then we have the rule itself. So I'm a config map, somebody tried to modify me, and we contain private credentials. So what will happen is we'll get the alert that a config map was created with private credentials, we'll get who did it. The other interesting thing is we'll also get the entire config map as well, and all the data in the config map. So what this does, if you did actually store a secret in there, we've now leaked your secret, and we're forcing you to rotate it. We should probably obfuscate that. That's another area of opportunity if somebody wants to contribute. All right, so I'm going to talk about installing real quick. In the Kubernetes world, we can install via Helm. We also have Linux packages as well. Helm is one of the preferred ways, lots of configuration options. And then we're also working on Falco CTL install as well that will install Falco into your Kubernetes cluster as well. So let's talk about how we use Falco, and I'll demo this real quick. So we wrote something called the Kubernetes Response Engine with security playbooks. What it does is it allows you to react to these events. So we have a number of different playbooks. You can kill an offending pod. You can taint nodes to prevent scheduling. You can isolate a pod with networking policy and so forth. So that then when this container goes rogue, you can keep it around, but isolate it and then go in and do forensics on it as well. You can subscribe to different level of alerts. You can subscribe to individual alerts. And so what this allows you to do is you can have different actions that take place depending upon the alert and severity. So what this looks like is that we publish into NATS, and then from NATS, kubeless picks it up, runs a small function, and then we'll take action on the particular function, or on the particular offending container. We have the same thing for AWS. We have the same thing for GCP as well. So this is another area to contribute. We're written in C++, and then we're starting to write more stuff in Go. And so if you're not comfortable with C++, we have a lot of YAML that you can write. And a way to contribute to the project. So let me go to this slide real quick, and then I'm going to jump into the demo. So, oh wow, it stayed up. So I'll just do a git pods, and you can see that Falco's running here. And I can do a kubectl logs, Falco. And I can see that there's been some events that have happened. We can see that a terminal was spawned in a container. Ignore this because I don't have this tuned for this particular machine. You can see that the bash history was deleted and other information like that as well. You notice that this is in JSON, so it's programmatic, so you're able to parse it and send it into another system. So what I'm going to do here is, let me just do a kubectl get pods again. And you can see that I have this Nginx deployment there. So I'm just going to do a kubectl exec. There we go. And my deployment name is wrong. And I'm just going to get in this container to start manipulating it and changing things and doing stuff with it. And I can't. And the reason why I can't is because what's happened is immediately within a matter of milliseconds, that function was triggered, and it kicked me off of the container. And it didn't, not only did it kick me off the container, it actually deleted the container, and you can see that that containers went away and a new one's been deployed. So this is what you can do with Falco, and we really think that it's important that you need to look at this entire, as you're looking at your DevSecOps security posture, looking at this entire workflow, looking at your DevSecOps pipeline and templating it and making sure that you're putting all the layers in place. But then also it's important to actually watch what's happening in production so that you can then, because everything that happens in production, all of this has to feed back into your development cycle. So the reason why that yellow line ends up continuing on is because whatever you discover, whatever malicious activity you might discover, then goes into patching something in your environment and working through that DevSecOps lifecycle. So if you have the Jenkins templating engine, if you're able to actually more easily go and incorporate those changes in and those feedback loops in, the faster that you can move overall in your pipelines. So with that, thank you very much. These are QR codes to our documentation. If you have questions, we'll take questions offline because we're right on time. But Stephen and I will be around. But thank you all for attending.
Thanks, everyone.